right, so let's look at an example where we're given a function and we want to find the derivative. And we'll use the limit definition that we talked about in the last section, and it was mentioned at the beginning of this section. So f prime of x, and we kind of did this with problems in the last section, although we were just kind of looking at individual points. Here we're getting an actual formula for the derivative that we could put any point in that's in the domain. So we had the limit as h approaches 0 and f of x plus h minus f of x over h. And so that's our formula. And now let's just plug everything in. So we get 8, and we're going to plug in x plus h in for each of the x's here. So 8 times x plus h minus 2 times x plus h squared, and then minus 8x minus 2x squared. And all of that is over h. And so now it's just a matter of simplifying and then taking the limit. So let's simplify the numerator. So we have 8x plus 8h minus 2, FOIL out the x plus h squared. So we have x squared plus 2xh plus h squared minus 8x minus 2x squared. And we have over h. And then simplify again, simplify more. Distribute this 2 minus 4xh minus 2h squared, and actually that should be a plus. And like I said, when we've done these difference quotients before, this is just the difference quotient that we've seen a couple times now. Anything without an h should cancel out. So 8x cancels with the negative 8x, negative 2x squared, the 2x squared. And so we're just left with the 8h minus 4xh minus 2h squared. And then you can either factor out the h in the numerator, or you can just cancel them out. Either way, we'll factor it out. So factor out the h on top. We have 8 minus 4x minus 2h, and all over h. And actually, we don't need to write the limit again. We can just cancel the h's. And, well, we'll add in the last little step. So 8 minus 4x minus 2h, plug in 0. So this is obviously continuous over all values of x and all values of h. Plug in 0 for h, and then we're just left with 8 minus 4x. Okay, and so that is the derivative. And so we can plug in whatever value of x we want from the domain, which of course, in this case, the domain is all real numbers. So we can plug in any value of x and we can get the derivative at that point. So that's how you do it. And we kind of saw examples like that in the last section. So it's not really too new, it's more conceptually new in that we can now get the function. All right, this one, so let's find the derivative g prime, and this one is actually easy. So the derivative of a linear function is just the slope. Remember, derivative means slope. If we have a linear function, the slope is always constant. And so the derivative is just going to be the slope. And you can work out the difference quotient if you like. It's not really necessary. But if you want to kind of prove to yourself that that is the derivative, you can. So now if we draw, we'll draw both graphs. So graph of g of t, we have a y-intercept of -5, we have a slope of 3, so it'll look something like that. And then the graph of the derivative, it's linear, so it has a constant slope. In this case, the slope is 3, so there is the derivative. So pretty simple as far as that goes. Again, the slope of a linear function is constant, so the derivative is just going to be a horizontal line. All right, so when can functions not be differentiable? So there are three examples here, and it helps, again, different derivatives, differentiability is talking about the slope, and slope at the tangent line in particular at any particular point. And so basically the thing to remember with some of these, I guess with the first two especially, is you want to make sure that you have a smooth curve. So for it to be differentiable, you need a smooth curve. This one is not smooth because it's got this little corner. When we're talking about derivatives, we can't abruptly change slope. And so that's what happens here. We cannot abruptly change. This one, any point of discontinuity cannot be differentiable at that point. And then the vertical tangent line, the derivative is a function. And so if you have a vertical tangent line, that means that that would not be a function at that point as far as the derivative goes. So the derivative is a function, so we can't have a vertical tangent line. And so here's an example. So f of x equals absolute value of x. So the graph of that is a v. You remember that from algebra and pre-calculus. What is the derivative? So technically, if you want to, you can rewrite the absolute value of x as a piecewise function of negative x when x is less than 0, or x when x is greater than or equal to 0. And so you can see negative x is just that negative diagonal, and then the positive x is just the positive diagonal. And so that's where we get that graph from. Now, hopefully you recognize from the last page, this is not differentiable there because it has the sharp corner. And so if we graph the derivative, or let's find the derivative first. So that would be -1. So the slope of that line is -1. The slope of that is +1. And so if we graph the derivative, we'll have the line at -1 there. Let's put a hole there because it's strictly less than. And then we're going to put another hole here, again, because of the sharp corner. And so this one is continuous everywhere, but it is not differentiable everywhere. And so anytime the derivative is not differentiable, or anytime the derivative is not continuous, that will indicate the points that it's not differentiable. So I'll say that again. When the derivative is not continuous, any point where the derivative is not continuous, that tells you that the function is not differentiable. And so this is actually a very common theorem that will be helpful and useful to remember. The main way to say it, if a function is differentiable at a number, then it is continuous. But you can also flip it. So any theorem, any logical statement, you can reverse it and negate it, and it will still be true. So we can say it this way: if a function is differentiable, then it is continuous. But we can also say if a function is not continuous, then it is not differentiable. All right, so we'll stop here and we'll look at a couple more examples in the next video.